Hi students, today I am going to explain valency bond theory of coordination compounds, an important topic in chemistry. Let's see. So, what is valency bond theory? So, who proposed it? So, valency bond theory was propounded by or proposed by Pauling, and what it is based on? It is based on hybridization concept. So how the hybrid orbitals are formed, depending on that this theory is based. So what are its assumptions? Let's see. So what are its assumptions? First assumption is the metal ion. So whatever is the metal ion, we know what are coordination compounds. So the central metal ion will be attacked by the ligands to form a coordination compound. So the metal ion will have available number of d orbitals. They have available number of d orbitals that will be equal to the coordination for accommodating the pair of electrons from ligands. So from ligands, the pair of electrons it will accept, the metal ion will accept. To accept that, it will have available number of d orbitals or vacant d orbitals will be present. Then with the examples we will understand all these assumptions. Then the metal ion will use s, p and d orbitals for accommodating these electrons taking from ligands. And we can say that ligands at least forms one sigma orbital, contain at least one sigma orbital containing one lone pair of electrons. And whatever are the vacant hybrid orbitals of metal atom or ions overlap with the filled sigma orbitals of ligand to form LM sigma bond. So this vacant hybrid orbitals of metal atom or ion will overlap with the sigma orbitals of ligand to form LM bond, that is sigma bond is formed. So the d orbitals used in this hybridization may be outer d orbitals or inner n-1 d orbitals. The d orbitals may be outer d orbitals or inner d orbitals. Then the Hund's rule applies to electrons in non-bonding orbitals also. So we should apply Hund's rule, and the number of unpaired electrons are present in is paramagnetic. If unpaired electrons are present, it is paramagnetic. If no unpaired electrons are there, then it is diamagnetic. So number of unpaired electrons can be found from magnetic moment measurement. So from the magnetic moment measurement, we can find out how much number of unpaired electrons are there. So mu is equal to n into n plus 2 bm. So that is the formula to find out. And why we should find out the number of unpaired electrons? So that it will help to find the shape of the complex. So when the strong ligands are there, under the influence of strong ligands, it is possible that unpaired electrons may get paired up against Hund's rule also sometimes. So it will be explained in some examples. When we go to the examples, we will be understanding clearly all these assumptions. So let's see. First, octahedral complexes. So there are octahedral complexes, square planar complexes and tetrahedral complexes. I will explain one by one. First, let me see octahedral complexes. So these are formed by maybe D2sp3 or sp3d2 hybridization. So when the complexes are formed by D2sp3, then that are called inner orbitals, or when sp3d2, that is called outer orbitals. We can get doubt what is the difference between these two. So this is the d orbital which is present inside. So that is why first we are telling d. So D2sp3, and the d which is present in the outer orbital next to the next orbital. So d, that is sp3d2, that is outer orbital complexes. So when we go to the examples, we will understand what are inner orbitals and outer orbitals. First we will see what are inner orbital complexes. So in this inner d, that is n-1 d orbitals form hybrid orbitals with ns and np orbitals for bond formation. So now let's see the examples. So if we understand the examples, we will understand the content very easily. So don't skip and listen all the examples up to the end to understand the concept. So first one is chromium Cr NH3 6 3+1 ion complex. So Cr is nothing but chromium. This is the metal ion, and NH3 6 are 6 ligands are attached to it. So this 3 plus is charge oxidation number. So chromium is, its atomic number is Z is equal to 24. So I wrote the electronic configuration completely. 24, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1, like this. It is in the ground state. So 3d5. So 1, 2, 3, 4, 5 singly first, according to the Hund's rule and Pauli's exclusion principle, first singly occupied and first lower energy is occupied. So 3d5, 4s1, it is in the ground state. But chromium they gave +3 oxidation state. So 3 electrons should be removed to get positive +3 oxidation state. 3 electrons should be removed. So we are removing 1, 2, 3. These 3 electrons we removed. So chromium +3 state will get 3d3 and all will be vacant. Then so when the ligands, NH3 ligands are attacking, then it will, there are vacant spaces to fill the electrons which are given by ligand. So 1, 2, 3, this will be like that only, and this NH3 will be attacking these orbitals. So the d orbital is inside. When it is after 4p, then it is outside. So this is inner orbital complexes. So as you understood, if it is 4d, after 4p when we are using the orbitals, then it will be outer orbital complexes, but we are using here inside 3d. Yes, no, that is why it is inner orbital complexes. So 1, 2, 3, 4, 5, 6, 6 places, 2d, 1s, 3p. So D2s P3, this much is vacant to be occupied with the ligand, attacked by the ligands. So 6 NH3 ligands will be occupied. So to form octahedral structures. So the geometry of this is octahedral, and because of the presence of unpaired electrons in the 3D, it is a paramagnetic in nature. Like this we can tell. Next, one more example I am giving. FeCN6 4-. So Fe is nothing but iron. We know that its atomic number is 26. So I wrote the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So in the ground state 3d6, 1, 2, 3, 4, 5, 6. Here 4s2. So in the ground state, and it is having, Fe is having +2 oxidation state. So we will remove electrons. So we can remove only these 2. But what happens, we want 6 CN to be attacked, 6 CN ligands to be attacked for the Fe. But if we remove only this one, then only 1, 2, 3, 4, only 4 places will be there. So only 4 CNs can attack, but we want 6 places. So 6 vacant orbitals we want. That's why 3D electrons are forced to pair up. So here 3D electrons are forced to pair up because CN is a strong ligand. So a strong ligand, it will force the 3D electrons to pair up. So these 2 electrons will get pair up here. So all the 1, 2, 3, 4, 5, 6. So these are paired, and we'll get 6 vacant orbitals: 1, 2, 3, 4, 5, 6 for accommodating 6 CN ligands. So the hybridization, as we expected, D2sp3. So D2sp3 is the its hybridization. And what is its structure? Octahedral structure. And because no unpaired electrons, all are paired, it is diamagnetic in nature. So next, one more example. FeCN6 3 minus, the same only with oxidation state different I'm giving. Before I gave FeCN6 4 minus, so here I am giving FeCN6 3 minus. Let's see again. Iron, its atomic number is 26. We wrote the electronic configuration. So ground state, it will be 3d6 4s2 as I wrote before also. Then 4e plus 3 ions, so 3 should be removed. So 1 2 and the pairing 1 is removed, so all unpaired electrons are there, and we have only 1 2 3 4 vacant places. But how many Cn should be there? Ligands should attack there 6. So 2 more places we want. For that, all should be paired. So 1 2 3 4 5 should be paired. So these 2 electrons will come and pair here. So 1 2 3 4 5. So all these are paired and 6 vacant places are there now. Again, so Cn will be occupied with this. This is also D2sp3 hybridization, as it has octahedral arrangement. So, and also it has one unpaired electron here. So we can say it is a paramagnetic. When no unpaired electrons, diamagnetic. When unpaired electrons are present, it is paramagnetic. Remember this. Then one more example. CrCO6 complex. So chromium, its atomic number is 24. So again we will write the electronic configuration. So 1s2 2s2 2p6 3s2 3p6 3d5 4s1. So 3d5 all are singly occupied, 4s1 singly occupied, 4p it is not there, empty. So in the excited state, what happens here? They didn't give any number, so oxidation state is 0. So nothing is removed, electrons. Then what happens? The electrons are forced to pair up. So these 3 electrons are forced to pair up here to make the orbitals vacant. So 1 2 3, these 3 are paired to these 3. So these 3 are paired now, ready for the hybridization, and all the 6 CO ligands are attacked the 6 places, like D2S P3, 2 places of D, 1 place of S, 3 places of P. Then so 6 CO ligands are attacked to the 6 vacant orbitals. Now tell me which structure it will be having. Geometry, as usual we can say octahedral, because we are discussing octahedral only. So octahedral geometry. And is it diamagnetic or paramagnetic? It is diamagnetic, because no unpaired electrons are present, all are paired. Then up to now we discussed inner orbital complexes. Now I will explain what is outer orbital complexes with the examples. So in this again NS, NP and ND, the DR, outer d orbitals are involved in the hybridization. Let's do with the example. COF6 3 minus. So CO is cobalt, its atomic number is 27. So I write the configuration. Every time I am writing the electronic configuration fully, so that we will not get any confusion. Just we will use the valency electrons outside shells only. So 1s2 2s2 2p6 3s2 3p6 3d7 4s2. So like this we got so 3d7 1 2 3 4 5 6 7 1 2. So and here it is CO3, means 3 oxidation state, as it is 3 minus here. So we should remove 3 electrons. So 1 2 3, first unpaired electrons, this 2 and this one we removed. So we will get like this. So 1 2 3 4 5 6, and how many are vacant? 1 2 3 4, only 4. But how many ligands are there? 6 are there. So 4 unpaired electrons can form bond, as 4 is a 4 unpaired electrons can form bond. And when we see F, it is a weak ligand. It cannot force the electrons to pair up here like in before. Yes, no. So before what happened? They are for like a CN. So it as it is a strong ligand, it forces it to pair up in 3D. But as F is a weak ligand, so it cannot force the electrons to pair up in 3D orbitals. Then what it will do? It will use the next orbital, that is after 4p 4d will come. So that it will use. So let's see. So F 4d orbitals are involved in hybridization. So CO F6 3 minus 3d will be like that only. SP and 2d of outside. So that is why it is outer orbital complexes. So outside 2d orbitals will be used by it for 6 Fc ligands to occupy. So it is a octahedral, as we know, and paramagnetic in nature. Why? Because of 4 unpaired electrons. Then next one is manganese, MnC2O4 3 minus 3H2O, a big complex. So Mn is nothing but manganese. So its atomic number is 25. I wrote the electronic configuration: 1s2 2s2 2p6 3s2 3p6 3d5 4s2. So 3d5 4s2 all are singly occupied here, see. And Mn 3 plus, so 3 electrons should be removed, 1 2 3. So from last we should remove every time. So 1 2 3 is removed, so 4 will be there. Then so MnC2O4 3 minus 3H2O, how it will form? So as it cannot force these electrons to pair up, as I already told, because it is also a weak ligand. So what happens? It will take the next d orbital, uses the next d orbitals for the vacant 6 electrons. So 3 plus 3. So different are there, different ligands are there, 3 C2O4 are there, 3 H2O are there. So what happens? 1 2 3 4 5 6, and the hybridization is sp3 d2 hybridization. So like this it will uses the ligands to occupy, and its structure is octahedral, as I already told, and 4 unpaired electrons are present in the 3d orbital. So it is a paramagnetic in nature. Then tetrahedral complexes. So first example for tetrahedral complexes is nickel carbonyl NiCO4. So nickel, as we know, its atomic number is 28. So 1s2 2s2 2p6 3s2 3p6 3d8 4s2. So I wrote in ground state 3d 8 4s2 4p which is vacant. So as the no oxidation number is present, so 0, so we don't remove any electrons. Now let's start doing directly. So 4 carbonyls should attack. So here 3 places are there. So what happens? These 2 electrons are jumped to here to pair up. So 4 vacant orbitals should be there first. So 4 CO. So it pushes the electrons from 4s orbital to 3d. So we'll get a tetrahedral structure, and the hybridization is sp3 hybridization. As no unpaired electrons are present, it is a diamagnetic in nature. So like this we can discuss. Next, one more example I am giving for tetrahedral complexes. ZnCl4 2 minus. So zinc is 30. I wrote the electronic configuration: 1s2 2s2 2p6 3s2 3p6 3d10 4s2. As 2 minus is there, so 2 electrons we should remove. The last 2 electrons we removed from S. So S and P are vacant. So 4. So 4 chlorine atoms, it easily form bond. So no need to push electrons or something here, because already 4 vacant are there. So ZnCl4 2 minus. So it will form sp3 hybridization. As no unpaired electrons are present, it is diamagnetic in nature. Then square planar complexes. So one more example I am giving. So I gave two examples from square planar complexes. It is similar to tetrahedral complexes. Let's see. Cu NH3 4 2 plus. Same again, copper will write electronic configuration 1s2 2s2 2p6 3s2 3p6 3d10 4s1. So in order to accommodate the 4 electron pairs donated by 4 NH3 ligands, so 4 vacant hybrid orbitals must be available. So for this there are 3 possibilities are there. What are they? Let's see. So first possibility is, so what happens, Cu 2 plus, so here 3d10 4s1, so when 2 electrons are removed, it will become 3d9 4s0, right? So 1 2 3 4 5 6 7 8 9, 3d9 4s0. So because 1 is removed from this, so 4 vacant orbitals are present, so s and 3p orbitals. So sp3 hybridization takes place as I explained in the tetrahedral same. So tetrahedral structure will be present, and it is because of no unpaired electrons, it is paramagnetic in nature. So second possibility if we see, so 3d9 4s 3d10 4s1, in this 2 electrons are gone, so 3d9 4s0. so in this 1 electron which is present, it will be pushed here, so it will be used, this d orbital, vacant d orbital is used for hybridization. So 1 2 3 4, so 4 it can bond, so it is dsp2 hybridization, and the structure is square planar, and because of presence of one unpaired electrons, it is paramagnetic in nature. Then third possibility, how it takes place, see again the same 3d9 4s0, so it will be taking sp, but it will remain vacant, and 1d orbital it will take from here. So sp2d it will take, it is dsp2 using this, but it is using outer, so sp2d. So these are the 3 possibilities that it is using for hybridization. So when it is using sp3, we will get tetrahedral structure. When it is using dsp2 or sp2d, it will getting square planar structure, and both are having paramagnetic type. All are having paramagnetic type because of presence of an unpaired electron. So one more example I am explaining now. Nickel cyanide, so NiCN4 2 minus. Nickel, as we know, it is 28 atomic number, so 3d9 4s1, so 2 electrons will be lost, so 3d8 4s0. So in the ground state it will be like this, 1 2 3 4 5 6 7 8, and 4 is 0, this is also vacant. So in the excited state what happens, this electron will come up and pair here, so we'll get vacant orbital, this one, so 1 2 3 4 5, so we'll get 1 2 3 4, sorry 5 will be there, in that 4 will be used, so dsp2. So it is also a because of sp2d or dsp2, it is a square planar structure, we'll get a square planar geometry, and also it is diamagnetics because it is all paired. So now one more example, manganese MnCl4 2 minus. You only have to try it and message me. So how the structure will be formed, and whether it is diamagnetic or paramagnetic, and the structure. So next, so like all theories have some limitations, even valency bond theory also have some limitations. So it this theory is unable to distinguish between D2 sp3 or sp3 D2 or dsp2 or sp3 something, because on the basis of number of unpaired electrons we cannot distinguish which hybridization it is taking place, and even it cannot explain the color of the coordination compounds formed, and even the magnetic property predictions are also not that much accurate, and it didn't explain why inner orbitals, outer orbital complexes forms, what is the reason behind it. It didn't explain properly, and it always ignored orbital interaction in this hybridization method. So these are the limitations of VBT theory. Just listening you can't do this. So you should practice all the coordination compounds, so from one by one of all the examples, so that we'll get one clarity of this theory. Thank you.